Alrighty. Okay, so today we got two types of identities that we're going to have to learn. They are our double angle identities and our sum and difference identities. So double angle identities, if you have sine of 2 times theta, that is going to equal 2 sine theta cosine theta. Okay, so that one is one that will be on your quiz. And then cosine of 2 theta is going to equal cosine squared minus sine squared. So those two right there will be on your quiz Wednesday. You must have them memorized.
For those of you got two that you said you hadn't taught us yet.
Right. Well, there's going to be 4. There'll be these 2, and there'll be 2 more on a later slide for those. But this is the reason you couldn't do number 15, because we did not know that identity yet. So let's look at what some of these questions will look like. The function k is given by k of x equals 4 cosine of 2x. Which of the following is an equivalent form of k of x? So right here we have cosine not of x but of 2x. So all we're doing is replacing it with the identity. And our identity told us that cosine of 2x equals cosine squared x minus sine squared x, right? That was the identity that was on the prior slide. So we are just taking this cosine of 2x that's right here, and we're replacing it with that cosine squared x minus sine squared x. When you do this, it is important right here, your k of x is going to equal, you need a set of parentheses right here, because you're replacing this with the whole thing right here. So cosine squared x minus sine squared x. And then if we look at our answer choices, which one is going to be correct? It's going to be D, because you'll just distribute that 4 right there, and you will get 4 cosine squared x. Oh, wait, no, hold on. What am I thinking? It's not D. Why is it not D? Oh, 4 sine squared x. Is that an answer choice? Oh, no, it's not an answer choice. In fact, I really should mark out D, because there's no way you're going to change that minus just to a plus, right? There's no identity that's going to let that happen. And I'm pretty sure it's not A. Why would it not be A?
They're like flipped.
Because they're not squared.
They're not squared, and this is the rule. Whoever did this one used the rule for sine, right? Sine is 2 sine x cosine x. And so this is what you would get if you use the rule for sine of 2x, which is not what you're supposed to use here because you have cosine. So I don't think it's going to be A, which leaves me with B and C. And in B and C, what is missing? What do you not see? You don't see a sign, right? So that makes me think probably we've changed that sine squared x so that it's not sine squared x anymore. What could we change sine squared x to? 1 minus cosine squared x. So if we do that, we'll have 4 cosine squared x minus 4 times 1 minus cosine squared x, like that. And we will need to distribute our negative 4. So we'll have 4 cosine squared x minus 4 plus 4 cosine squared x. And then these cosine 4 cosine squared x's, I can put those together. That will give me 8 cosine squared x minus 4. And that is C. Okay, you have to let your answer choices sort of lead you where to go on that, because we could have changed cosine squared x to 1 minus sine squared x, but then we would get only sines, and we don't have an answer choice that's only sines for that. So So kind of look at your answer choices to decide where you need to go. Take it a step at a time. First thing, obviously, you're going to need to replace this, but then you might not get the answer choice that is there, so you got to keep going for that.
So instead of having to do all that, can you just like look at the formula and see that the cosine comes first?
Not necessarily for that, because, for example, if we had like a -4 right here instead of a +4, it would switch which one comes first. So you do really need to work it out, because depending on what signs you have in different parts, it could still be, it could be B right here. Like if that was a -4, you would get B for that. All right. So it's a lot like what we were doing on Friday. It's just we're throwing another identity in there that we know. Let's get rid of that. Let's go to the next slide. Okay, here is a different type of problem. Here it says, which of the following is equivalent to the expression 2 sine pi over 14 cosine pi over 14? Now, which formula does that one look like? Does that look like the sine formula or the cosine formula? Sine. So that sine formula says, the one we're thinking of here says that sine of 2 times an angle would equal 2 times sine of the angle cosine of the angle, right? So in this case, your pi over 14 is your theta, right? So this would be equal to sine of, not pi over 14, what would it be? So like right here, what they've given us is, we know these two angles right here, right? We know those are both pi over 14, right there. So we know those angles. So that means this right here is also pi over 14. That's being multiplied by 2, right? So we would have to write this as 2 times pi over 14. And if I want to multiply that together, I'll put that over 1. And I will get sine of 2 pi over 14. But that will reduce, what does it reduce to? Pi over 7. And so C is going to be my answer for that. So that one, you're kind of taking your formula here and working backwards to get that double angle for that. Any questions on that part? All right, moving on. I think these are the more difficult ones that he has put in these notes. I kind of made my own notes, but this one came from Mr. Passwater's notes. Did I put that at the beginning of these notes?
So why do you have to put the
Yeah.
adapted from him?
He just wants you to give credit. So like, you know where it came from. It's more like, because teachers a lot of times will like pass this on to other teachers. Like I usually, like let's say that Miss Martin ended up with a section of AP Precal, I would give her all my stuff so she could use it. And she does the same thing for me. So it's just kind of good to have it like where this came from, so that like 3 teachers down the line, we're not like claiming everything as our own, and it's not really. So so I just throw that on there if I've got anything from his notes on there. I don't think he I don't think that he would be like, you'd be in legal trouble necessarily, unless you were trying to make money off of it. Like, for example, you could take this right here and make yourself a good teachers pay teachers worksheet and try to like sell it on Teachers Pay Teachers, and like if you've stolen his stuff and you're selling it on Teachers Pay Teachers, he might be upset about that. But if you're just using it in class, he doesn't mind. But I think that he's just trying to avoid, like,
He's just trying to be helpful.
yeah. I think he wants you to say where it came from so that you can't pass it off as your own and possibly monetize it on down the road. Because he is being very nice by not monetizing any of his. Like he's not selling it. You just can use it free. So he doesn't want somebody taking all of his hard work and selling it and making money off of something that he did, which I can't blame him for. I can't even imagine how long. Making these stupid pictures takes forever.
Why does he not make money off of it? Why is he just giving it out for free?
Because he believes in the good of education and really wants it to be free for everybody to use, which is so nice. Because, in fact, they were like, on my Facebook group, they were like, Brian Passwater, you should write a textbook. And he like responded and was like, but if I wrote a textbook, then it wouldn't be free for everybody, and not everybody could use it. So he like doesn't even want to do that. So he's a really nice guy.
What does he look like?
I don't know. Let's Google him real quick. Let's see. I don't know. Hold on, I'm still. Okay. So we have a circle centered at the origin. Oh, I've cut my screen off because I was Googling things, and it's always a little dangerous to be Googling things with your screen on for that. So just the ads sometimes will get you on that. So, all right. So the figure of a circle centered at the origin with an angle of measure theta is in standard position. The terminal rate of the angle intersects the point at point P. Coordinates of P are 5, 12. What is the value of sine 2 theta? So, in order to do this, we're going to have to use the formula for sine 2 theta. And that formula for sine 2 theta is going to be 2 sine of theta cosine of theta. So, to do that, we're going to need this picture right here to figure out what sine of theta and cosine of theta are. Now, these are not unit circle numbers right here, so the unit circle doesn't really help us here, but we do know if this point right here is 5, 12, then that means that your x value, the length of this side right here, should be 5. And then your y coordinate is 12, so that's how high you would go. Like, think about just graphing this point, right? If you got the point 5, 12, you go over 5, you go up 12, right? So this side right here would be 12. And what is the radius of that? It's 13, because it should be the same. You could either do Pythagorean theorem, or it should be the same as this coordinate over here. So I can find sine, cosine, or tangent of this function because I know what the triangle looks like, right? This is what the triangle looks like. So sine of theta is going to be sine. We got to think sort of back to our triangle trig. Sine is opposite over hypotenuse, which for this problem is 12 over 13. So, sine of theta, which is what we need here, right, equals 12 over 13. The whole thing, not just the angle, the whole expression, sine theta is 12 over 13. So we can plug in 12 over 13 here. And then, if we go over here, do the same thing. We need cosine. So cosine of theta is going to be our adjacent side over our hypotenuse. 5 over 13. Very good. So if we look over here for that, this is our cosine. Right here with cosine, it equals 5/13. So we plug that in. Here, it's over 1. And so you would just multiply straight across from that. I don't think anything's going to cancel. I'd do 2 times 5, which would give me 10. Multiply by 12, you get 120 on the top. 13 times 13 is 160. Is it 169? I think. Is that right? 3 times 13. Somebody check that. I think that's right. Okay. All right, and that would be our answer. That's our value of sine of 2 theta. Okay. You're going to see on this, you might get questions about cosine 2 theta. You do the same thing, you just use the other formula for that in that case. All right, questions? All right, here is an equation for this. So this one's asking us to solve an equation. It asks for principal values of x. I pulled this from an old worksheet that I had. Best I can tell, they're not going to do that really on the AP exam. They're usually going to do 0 to 2 pi. Principal values, though, are those values for whenever we were doing our inverse trig. Principal values, in case you see it, principal values for sine and tangent, you would be looking from negative pi over 2 less than or equal to x less than or equal to pi over 2. It's the first and fourth quadrant. We did it whenever we were doing the inverse trig. And then for cosine, you would use from 0 to pi. So that's what it's asking when it says principal values. I haven't seen a lot of AP material where they did that, but our old textbook used to do it, and my old stuff has this, so I'm going to throw it in just in case it shows up. You've seen it before. So it doesn't really change how you do the problem any. It just changes where you're looking for your answers. Instead of looking at the whole unit circle, we'll just look at these parts right here. So this problem is sine of 2x minus 1 equals 0. So we might think that we should use that new formula that we just found. So if you do that, I would not write this down because it's going to be a dead end. Then I would have 2 sine x cosine x minus 1. I wouldn't write this part down. I'll tell you when I would start writing. If I do that, if I use the formula, then can I factor that? I don't have any squares. I don't have a greatest common factor. I could move the 1 over to the other side, but I can't split things up with that sine cosine. So it actually, on this one, does not help to use your identity on that. And I put this on here on purpose to see the 2 different ways you can deal with it whenever you got that sine of 2x. So what we're going to do here instead is we'll move the 1 over and we'll have sine of 2x equals 1. And we did a little bit of this whenever we were looking at, where the vertical asymptotes were on our secant and cosecant and whatnot. Because we might have like cosine of 2x equals 0. It was always 0 when we were doing vertical asymptotes because if the denominator is 0, you have a vertical asymptote. For just solving an equation, it might not equal 0. It might be another value. So if I want to solve this for my x, I need to do sine inverse, right? To get rid of that sine. And that sine inverse of 1, remember, is asking me where does sine theta equal 1. So where on the unit circle does sine equal 1? pi over 2. Okay? And then I am going to have 2x equals pi over 2, not just x equals pi over 2. So I would need to divide by 2 here, or I would prefer to multiply by 1/2 because I got a fraction over here on this other side. And 1/2 times 2 cancels out because it just equals 1. And over here I'll get pi over 4. And that is between negative pi over 2 and pi over 2, so that works for our answer right there. So sometimes you might see something that we could use an identity for, but it actually doesn't help us to use the identity. However, I think my next one we do need to use our identity for. Okay, this time we're looking at the whole unit circle, and this time I've got a sine x right here, and I've got cosine of 2x over here. In this case, we're not going to be able to do like we did on the last problem because this is not just equal to a number. We got some other expressions here. So since we have those other expressions, probably we're going to have to use that identity for cosine of 2x. And that cosine of 2x, it equals cosine squared x minus cosine, minus sine squared x. Cosine again, that'd be 0. Like that. So we can take cosine 2x out, and we can replace it with cosine squared x minus sine squared x. So we got 1 minus, or negative 1 minus 3 sine x equals cosine squared x minus sine squared x. And once we've done this, it really takes us to the problems that you guys were doing over the weekend on that last section. What do you think we should do? Try here. I can.
Change everything to sine.
I think we need everything to be sine because we're not going to be able to factor this with the sine and the cosine there. And why did you choose sine instead of cosine on that? There's already... especially the one that really matters is this sine right here because it is not squared, so we're not going to be able to change it to cosine. So let's go everything to sines, which means that we are going to do this. Cosine squared is going to become 1 minus sine squared x, and then we'll still have this other minus sine squared x over here. And I would put those two sine squared x's together, so that will give us 1 minus 2 sine squared x, because it's like you got 1 with each one of them and you're just combining your like terms. What do you guys think now? We do want to factor, but before we can factor, everything has to go to one side. I would move everything to the left side. It will be easier to factor if your sine squared is positive. So I would move this plus 2 sine squared x plus 2 sine squared x over here. I would subtract that 1 right there, and I would write it in order. So I'd have 2 sine squared x. I'm going to put the minus 3 sine x next. And then we'll have a minus 2. 0.
Where does the minus 2 come from?
The negative,
sorry,
yeah, this is a negative 1 minus 1, which is
Yeah.
going to give you a negative 2 instead of canceling. Yeah. Okay, so now we want to factor. We got 3 terms, so this is going to be 2 sets of parentheses. This is also going to be that more difficult factoring because we got that 2 in front of our sine squared. So we have to do 2 sine x here and a sine x here. The only things we can multiply together to get negative 2 are negative 1 and 2, or possibly positive 1 and negative 2, right? But those are our only options. So it matters a lot where they're at. We're going to have to check for that. So for example, if I just put a negative 2 plus 1, and then I check what I would get negative 2 sine x here in the middle. I would get a positive 2 sine x here, and those would add together and cancel out, and I wouldn't have a middle term at all. So is that correct? It is not. So let's switch where they are. Let's put the 1 right here and the 2 right here. And so now that, whenever we check, negative 1 times sine will give me negative 1 sine. And then 2 sine times 2 will give me 4 sine, which is going to give me positive 3 sine x. Is that right? No, but we're really close. We just need to change our signs, right? So let's make this one a positive and this one a negative here. And that will give me a positive 1, a negative 4, which gives me a negative 3 in the middle. So now we have it factored correctly. We should have 2 sine x plus 1, sine x minus 2. Okay, there. All right, and then we're almost there. We'll have 2 sine x plus 1 equals 0, and sine x minus 2 equals 0. Over here, that's going to be 2 sine x equals negative 1. We'll divide by 2. Sine x will equal negative 1/2. And over here, we'll get sine x equals 2. Did I get any answers from that? Sine does not equal 2. It's too big, so although you've done it correctly, that doesn't give you any answers. We would just look for where sine equals negative 1/2. Where does that happen? Seven pi over 6 and 11 pi over 6. And those would be our two answers for this one. You should notice, really, that first step is the only new thing. The rest of it is stuff that we did on the first part of it. Hello? Yes, thank you. Bye. Lexi, you are leaving. Let me give you your worksheet. Okay. All right, so that's all using the double angle identities. Let's look at the sum and difference formulas. I think that these are harder to memorize, but I think it was Miss White, or was it one of my teachers? I can't remember. I think Miss White used to do this. Anyway, there are songs, well, little, I don't know what you call them, little ditty to help remember these, which really helps me, and I can remember them pretty well because of the songs. So I'll start with cosine down here because I like it better. With cosine, if you'll notice what the formula looks like, x and y here would be angles. And you've got cosine of x plus y. It could be like pi over 3 plus pi over 6 or something here. Or it could be a minus. It's going to equal cosine x, cosine y. Look at this sign right here. What's weird about it? It is upside down, and it has to be upside down because what it's telling you is if it was positive here, you're using a minus here. If it was negative here, you're using a positive here, right? So the sign changes, whereas that's not the case for this formula, right? Notice it's the same, which means if it was positive here, you have a positive here. If it was negative here, you have a negative here. And then you got sine x, cosine x. So I'm going to give Miss White the credit for this. I know I did not come up with this, but I think it was her. She would sing the cosine conga for this. So you got to do the cosine conga. which is, like that. And it is cosine, sine, sine. Don't forget to change the sign with the G, the sign in the middle. So to sing it, you got to go, you can do your arms if you want here, but it's the cosine, sine, sine. Don't forget to change the sign. You kind of got to make it fit there at the end. But cosine, sine, sine. Don't forget to change the sign there. And if I were more coordinated, I'd do my motions there. You guys can work out a dance for that. So that really helps me memorize that, and I can sing it over and over to myself. And whenever I write it down, I write down cosine, sine, sine, and then change the sign in the middle. So that, I'm really good at remembering that one because I really like that little jingle, and I can remember it now. So hopefully that'll help you as well. The other one is pretty good too, and it helps me. I don't like it as much as the cosine conga, but it's more of like an army sort of chant here. It goes, let's see, it goes sine, cosine, sine, sine, cosine, sine. The sign of the sign is mighty fine. Meaning that the sign, S-I-G-N, the sign that you see here is of the sign function is mighty fine. So since it's mighty fine, you don't have to change it because it is what it is supposed to be. So you'll keep that same sign right here. So it's like, I wish I was better at this, but like sine, cosine, sine. The sign of the sign is mighty fine, like, like army chant there. So that helps me remember too. Although I think the cosine conga is cuter there. So those will be on your identities quiz on Wednesday, and you have to have them memorized for that. And we're going to need them, of course, to do these problems that are coming up. Yeah. So let's look at what questions look like for this. I honestly don't know if AP is going to give you a question exactly like this, but this is all our textbook used to do, and I think it's kind of helpful. If you go back to the dark ages when there were no calculators, which I realize always makes students angry that we're even discussing that possibility because it's not your reality, but finding sine of pi over 12 was not easy because it's not on the unit circle, right? That value is not on the unit circle. Now today, we can type it into the calculator and it will give us that value rounded to a close. It's going to be accurate enough for us to do pretty much anything we need to do with it. But if you needed to do this in the ancient days, that would not be helpful. However, if I've got pi over 12, 12s are important because it would be the common denominator of the unit circle, right? If you think about our unit circle, our denominators, we've got, you got pi over 6, pi over 4, pi over 3, pi over 2, right? Those are your unit circle values. 12 is the common denominator of all of these right here. So if we think about taking these and getting a common denominator, pi over 6, we would have to multiply the top and bottom by 2, and pi over 6 would be 2 pi over 12. And then if we want a common denominator for pi over 4, we would multiply by 3 on top and bottom to get 3 pi over 12. For pi over 3, we would have to multiply the top and bottom of that fraction by 4 to get a denominator of 12. So that would be 4 pi over 12. And then pi over 2, we'd have to multiply by 6 on the top and bottom. And that would give me 6 pi over 12. And I could do the whole unit circle like this if I wanted. This will be sufficient right here. So if you are asked to find sine of pi over 12, then I don't know any unit circle values for pi over 12. But if I've got a couple options here, right? I could do 3 pi over 12 minus 2 pi over 12, and that would give me pi over 12. Or I could do 4 pi over 12 minus 3 pi over 12. Also, that would give me pi over 12. So really, you could just pick which ones you want to use here. We'll use this pi over 12 and 3 pi over 12. All right. So sine of pi over 12 could be written as sine of 3 pi over 12 minus 2 pi over 12. And let's, if I subtract them, I will get pi over 12, which is what I want. But I don't really want to do that. I don't want to go back to pi over 12 because that's not on the unit circle, and I can't figure out what it is. But if I reduce them back, this is sine of 3 pi over 12 is pi over 4, and 2 pi over 12 is pi over 6, right? I changed everything to 12s first to show you why in the world I'm using pi over 4 minus pi over 6, right? But pi over 4 minus pi over 6 does give us pi over 12. So once I have it broken up like this, I've got two angles and they're subtracted. So I can use my my sum and difference formula for sine. So for sine, that one's our army chance. This is the way I usually do it in my head. I'm doing sine, cosine, cosine, sine. Sine of the sine is mighty fine. That goes right here in the very middle, right there. So where I had a minus, I put a minus here. Sine stays the same. And then I'll go back and fill it in. This will be pi over 4. This will be pi over 6. Pi over 4. Pi over 6. There. Okay. Is everybody okay here? Now, all of these values are on the unit circle, so we can figure out what they are. So, at pi over 6, we have square root of 3 over 2, 1/2. And at pi over 4, we've got square root of 2 over 2 and square root of 2 over 2. So now we're just plugging in numbers or values from the unit circle. So sine of pi over 2, what is that? Root 2 over 2. Don't keep your sign there. Sine of pi over 4 equals root 2 over 2. You're replacing the whole thing. What is cosine of pi over 2 or pi over 6? Root 3 over 2. And then cosine of pi over 4? Root 2 over 2. And sine of pi over 6? Okay, so then this is usually going to be simplified a little bit. You can multiply together. If you have two things under the square root, you can multiply them together. So this is going to be square root of 6 on the top and a 4 on the bottom, but that 4 is not underneath the square root, right? And then over here, 1 and square root of 2, I can't really multiply them together, although it is a 1, so it really doesn't matter. So I'm just going to have square root of 2 right there. And on the bottom, I'll get 4. Since these are common denominators, they will probably write it like this. Square root of 6 minus square root of 2 over 4. you cannot subtract things underneath the square root. So square root of 6 minus square root of 2 does not equal the square root of 4. So we can't do that. We would just leave it like this. So if you lived in the Dark Ages and you needed to know the exact value of sine of pi over 12, you could do this and figure it out. I realize that that does probably not get you all that excited about being able to do this, but now you at least know. As far as sum and difference formulas, I don't know a lot about the applications of these. We pretty much just need to know how to use them. In this case, I'm not saying it's going to be the most useful thing that you've learned, but I do think they'll put it on the exam, so it will be useful if we get college credit for this class and don't have to take it over again. All right, example 7. I think, let's see. Is this my last one or have I got one more? Oh, I messed something up there too. I didn't copy the whole thing. Did I? No. Okay. Well, we're going to do 7, and we're not going to do the last one because I didn't even copy the problem right. Anyway. All right, so for this one, they like to do this sometimes. They give you an equation and they say find the value of f of pi over 6. What do I have to do to find the value of f of pi over 6?
Plug it in.
I just plug in pi over 6 into this equation, all right? That's all they're asking you to do there, right? So we're doing cosine of pi over 6 plus 2 pi over 3, right? And this would not be a calculator active problem. So you would have to figure this out without the calculator because it would be too easy if you just typed it in. So this one is a cosine. So we have to do the cosine conga for this. So as we're writing out the formula, I would say cosine, cosine, sine, sine. Don't forget to change the sign, which means we got a plus here. We want to put a minus right here. And then it's always, you'll always go in the order of the fractions there. So you got pi over 6, 2 pi over 3, pi over 6, 2 pi over 3. Like that. And so much like we did on the last problem, we're just pulling these values from the unit circle. So we need our values right here at pi over 6, which is square root of 3 over 2, 1/2. And we need 2 pi over 3, which is here. And that would be negative 1/2 square root of 3 over 2. For that. So cosine of pi over 6 is going to be our x-coordinate right here. That's square root of 3 over 2. Cosine of 2 pi over 3 is negative 1/2. And then we'll get sine of pi over 6, which is 1/2. And sine of 2 pi over 3, which is square root of 3 over 2. And if we multiply together here, that is going to give me negative square root of 3 over 4 minus the square root of 3 over 4. It might be helpful, putting these together might be a little bit confusing with the roots. It might be helpful to put like the 1 here and the 1 here. So when we do negative 1 square root of 3 minus 1 square root of 3, we will get negative 2 square root of 3. They're like common, they're like terms that you're putting together. And then the denominator just stays the same whenever you add or subtract fractions, so you'll just keep that 4. And then this will reduce. You got 2 over 4, so that would be negative square root of 3 over 2 right there. And that'll be your answer for that. So that